Good afternoon. I apologize for not making it to the meeting. My wife broke her foot last week, and so I've had to stay home and help her wrangle the kiddos. Okay, so as you've seen in previous talks, the peak and total RF power of a conventional multiband pulse increase with the multiband factor. So in this talk, I'm going to go through strategies that modify the multiband phase profile to try to control this. So I'll go through talking about first the phase profiles, and here there are various strategies that increase in the spatial order with which they modify the phase profiles, and these approaches are going to minimize the peak power of the profiles because they're not going to use any gradient modulation or in any way change the amplitude profile. You've already heard about strategies that modify the multi-slice amplitude profile, specifically pins pulses and multi-pins pulses. And these guys can minimize both peak and total power, but they require gradient slewing. Strategies that then I'll finish off this talk by talking about a strategy that modifies both amplitude and phase profiles to try to get much shorter multi-pins pulses. Okay, so to talk about zeroth order phase modifications, we need to understand the multiband modulation function. So to build a multiband pulse, you take a single band pulse and you can multiply it by a complex exponential that modulates it to each slice location in your multiband profile, and then you can sum those guys up to get the total multiband pulse. Now, since we have the same single slice pulse for every band, we can pull that out on the left-hand side here, and what's left over is the sum of complex exponentials. And this guy is the multiband modulation function. Now, if we look at this in the Fourier domain, what it is it's going to be a comb function where we have a spike at every slice location, multiplied by a rect function that selects out just the MB slices that we care about. And this guy is going to be proportional then we can analytically calculate the Fourier transform of this, which is going to be a sinc convolved with a comb function. So here I've illustrated the comb function as a function of space, where we have one spike for every slice in our profile, and we multiply that by a rect to select out just the slices we want. Then we take the Fourier transform of that, and you can see that you get these aliased sincs, essentially. And we can see that then we have these large main lobes in the sincs, and then the side lobes. And we can see this pattern then propagate through to a multiband pulse when we construct a multiband pulse from a single band pulse. We see these peaks and side lobes. Okay, so what zeroth order phase modification approaches do is reduce the peak to side lobe ratio of the multiband modulation function. So mathematically what we have here is that we add these slice-dependent phase shifts to the multiband modulation function that depends on the slice location. And there have been three different approaches proposed to do this. Eric Wong had one of the 2012 ISMRM where he numerically optimized the phases given a multiband factor. You can also just use an analytic expression. That's what I'm going to introduce in this talk, given here, where you take the phase as equal to some factor k, which I calibrated to be 3.4 over the multiband factor, and did that empirically, just times the normalized slice location squared. And then Shai and Malak at the last ISMRM gave constructed phases numerically, did numerical optimization to get the phases, and then constrained them to be Hermitian symmetric so that you get real valued pulses, which is nice for certain systems. And if we plot the peak RF amplitude that we get with each type of phase modification as a function of the multiband factor, you can see that Wong, which has the fewest restrictions, gives the lowest peak RF amplitude at every multiband factor. The quadratic phase pulses are a little bit lower than that, or sorry, a little bit higher than that. And then Molex sit on top of that, although I would say overall that you don't have to pay all that much with Molex to get the real valued pulses. One interesting thing to note here is that the phases do not depend on the slice gap. So you can calculate a table of these guys once and use them for every slice gap that you might run into in practice. So moving up one order in spatial phase profile, we get the time-shifting method. So now we're looking at linear phase profiles. So the basic idea is to shift the slices' waveforms in time so that their main lobes don't overlap. So here I'm plotting where I increase the delay between the subpulses in a multiband 5 pulse. And as I do that, you can see that for a given peak B1, if I scale each one to this given peak B1, that I can reduce the pulse duration by quite a lot. And you can see that you can then start to make out each individual slice's main lobe. But if you go too far, then the pulse duration starts to increase again, slowly. So there is a sweet spot here where we get the lowest pulse duration subject to a given peak B1, and the object of pulse design is to figure out where this minimum point lies. You can see that it tends to lie in a place where you have some overlap in the main lobes, but you can still make them out. Now what this is going to do is it's going to apply a different linear first order phase ramp to each band. And so you can see as you increase the shift per band that we have, if I plot the real part of the refocusing pattern of this pulse, you can see that the outer slices start to accrue large phase rolls, whereas the inner slices have lower frequencies. And then we can compare this to zeroth order phase modification using Wong's method. And you can see that for a relatively low time bandwidth product of 3, we get a little bit of an improvement, about an average of 15% shorter using the time-shifted pulses. But if we go up to a higher time bandwidth product of 6, we get a much larger improvement. So here about a third reduction in the pulse duration. And this is because the main lobes have a lot of side lobes that they can overlap onto. And you can also apply optimized zeroth order phase shifts, but I found that on top of the linear phase shifts, but I found that that empirically doesn't help all that much and requires a fair amount of extra computation. The thing again to note about these is that you're going to get a different ISO delay for each slice. So if you want to use them as refocusing pulses in a spin echo sequence, then you have to either match them up with a 90-degree excitation with twice the time shift, or you have to use them in a dual refocus manner so that the time shifts cancel. Moving up then to higher order phase modifications, one way to do this is the root flipping method that my lab published, and it's in MRM Early View right now. So what we do here is we observe the fact that the configuration of an RF pulse's complex passband roots, these are delineated here on the unit circle, that the position of them with respect to the unit circle, whether they're inside or versus outside, determines the position of its main lobe. It determines essentially the position of the spread of its energy. And so what we can do is we can construct a minimum phase multiband pulse, because generally that gives the sharpest profiles for a given duration. And here I'm plotting zooming in on the right-hand side of the unit circle, showing the passband roots of a 3-band pulse. And if we optimize the different root positions for these different bands, you can see that we can spread out the main lobes in time. So if we then have a minimum phase pulse for this band, that goes over to the beginning of the pulse. The top one is left on the end, and the middle one is linear phase. It puts it right about in the middle. So the roots can be flipped optimally to reduce the peak RF amplitude. And we can essentially do this just by going through and trying to find the best root flip pattern overall. We can compare this then to pulses that are designed by Wong's phases or by the time-shifted method. And what we find is that the pulses are always the shortest, subject to a peak B1 of 13 microtesla, which is a common body coil peak B1. The pulses are almost always shorter than 10 milliseconds, and they're about a factor of 2 shorter than time-shifted pulses. Okay, so now I want to combine these two concepts of doing both amplitude modification to the profile, that is pins or multi-pins type modifications that add slices to the profile and then inverse the pulse somehow to reduce the power. I want to combine that concept with phase modification. And one very straightforward, just first stab at this, is to, instead of using linear phase pulses to construct pins and multi-pins pulses, we can use minimum phase pulses. And on top of that, we can take it a step further and even add quadratic phase on top of the minimum phase profile. So here I've got a linear phase multi-pins pulse versus a minimum phase multi-pins pulse. And the minimum phase multi-pins pulse is able to excite exactly the same slice amplitude profile, but it is 27% shorter because a minimum phase pulse excites a sharper pattern for a given duration. Then what I did was I did a simulation of a bunch of pulse designs from MB factors of 3 to 13, spaced evenly over a 120 millimeter field of view that represents the brain. They all excited the same slice profiles, and they were subject to a maximum 18 microtesla peak B1. Some of them went lower than that. The pins and multi-pins went lower than that. And what I've plotted here is then the total power of the pulses and the duration of the pulses. So we can see that a conventional multiband pulse that we construct using zeroth order phase modification from Wong's method, that guy's power is going to increase as we expect as a function of the multiband factor. The pins, as is suggested by its name, is going to have a flat power as a function of the multiband factor. In all of the multi-pins variants are going to be somewhat below that, actually even lower than a single band pulse. Now, which is what these are all normalized to. Then the duration of the pulse is an interesting story. So here we have again that the multiband pulse's duration is going to increase with multiband factor. The multi-pins and pins pulse durations are superimposed on top of each other, and they actually decrease somewhat, and that's as you increase multiband factor, and that's because you get larger and larger gradient blips since you have smaller gaps between the slices for a given fixed field of view. Now what's cool here is that if we just switch to minimum phase pulses, we get a huge jump in pulse duration with only a small increase in total power. And then if we add on top of that minimum phase pulse, if we also add quadratic phase to give us overall a minimum plus quadratic phase multi-pins pulse, we can get even shorter pulses still and also get lower power than the conventional multi-pins pulse. So in all these pulse designs, I use the minimum SAR mixing ratio, which you can derive analytically as the norm squared of the pins pulse divided by the sum of the norm squared of the pins plus the multiband pulse power. Okay, so what we get here is a big win with the minimum phase pins pulses, and we get the lowest power and duration with the minimum plus quadratic phase pulses. I'll say that this minimum multiband power curve is representative of all the phase modification approaches since they all apply the same slice amplitude profile. But although you would get shorter durations with the root flip pulses, it would just essentially this curve would shift down somewhat and just cross the pins and multi-pins profiles or curves at a later point. Okay, so to finish up here, then I've put all the code to design all these pulses into a toolbox that I call MBRF Tools on my Bitbucket site, so you can download them there if you're interested. What we found is that peak RF power can be decreased by modifying the multiband phase profiles, and that we get the shortest durations with the root flip multiband pulses. And generally, though, as we increase the spatial order of the phase profile, we get more reduction in peak power. Total power can be decreased by modifying multiband magnitude profiles, and in general, we get lowest power with multipins pulses. Both approaches, though, can complicate sequence design. If you have larger than zeroth order phase modifications, you're going to need a matched excitation pulse or a twice refocused pulse to cancel that phase out. If you do amplitude modification with pins or multipins, you need some strategy to suppress the extra slices. Combining both, which we did with the minimum and quadratic phase multipins pulses, will give the lowest power while maintaining short durations of any of the methods. I don't think we've reached the bottom yet, though. I think there's still a lot of work here to do to derive practical ways to modify both of these and have them running on the scanners and get consistently short durations. And this is, in fact, a topic of the ISMRM RF Pulse Design Challenge, which I urge all of you who are interested to engage in starting this fall. And then I'll acknowledge my support. Thank you very much for listening.